We're now in section 2.4 and we're going to talk about derivatives of other trig functions. We've already talked about the derivatives of sine and cosine. We know that the derivative of sine of x is cosine of x, and the derivative of cosine of x was pretty close to the opposite of that, sine of x, or negative sine of x. And these two facts are just so kind of representative of how beautiful calculus is. The derivative of sine of x doesn't have to be cosine of x in our world, but it is. It could have been something really complicated like sine of, I don't know, something weird or complicated, but it's really elegant that the derivative of sine, you know, this curve that's doing that, its derivative is just, why don't you shift it over pi halves and you'll get cosine of x, and then the derivative of cosine x is simply negative sine x. And this is just another manifestation of how elegant calculus is. I mean, the derivative of e to the x being e to the x is kind of the pinnacle of how beautiful this subject is. But these guys are really strong contenders. So but we have other trig functions, and we need to talk about what their derivatives might be. You know, tan x is a trig function, secant x is a trig function, cosecant x, and then cotangent x. All of these, we do need to find out what the derivatives are. And we're helped quite a bit by the fact that each of these can be written in terms of sine and cosine. So you probably remember that tangent is just the same as sine over cosine. And secant of x is just 1 over cosine of x. And cosecant of x is just 1 over sine of x. And then cotangent is the reciprocal of tangent. That's cosine of x over sine of x. So we have these four trig functions that are really just combinations of sine and cosine. And now we put the fact that we know what the derivative of sine and cosine are together with the product and quotient rules. And here, the quotient rule is what we could use in each of these cases to find their derivatives. So we will use quotient rule to find each derivative. Each of these four additional trig functions, we can find their derivatives knowing what the derivatives of sine and cosine are and knowing the quotient rule. Okay, let's start with one of the favorite trig functions, tangent of x. So if y equals tangent of x, we want to find its derivative. And tangent of x, so we want the derivative of tangent of x, but the derivative of tangent of x, it's the same thing as sine of x over cosine of x, because that's what tangent of x is. And we're going to use the quotient rule. Here's the quotient rule right here from back in 2.3. And this would actually be a fantastic example for you to try before you see what the solution is. It'll give you good practice with the quotient rule, and you definitely have all the tools you need to find this derivative. So I'm going to stop the video and you try to do this on your own. Okay, so we're going to take a stab at finding the derivative of tangent of x, which we all know is just sine of x over cosine of x. And you've tried it, you've taken a stab at it. So let's just get started by using the quotient rule. The quotient rule says take the low cosine x, d high. So the derivative of sine x is cosine x, so that's times cosine x, minus high sine of x, and now derivative of low. So derivative of cosine x is a negative sine x, all over. And also, by the way, make sure you're using parentheses here so that it ensures that we recognize it as a multiplication and not a subtraction. Okay, over low squared, and low squared, that would be cosine squared. Okay, so cosine squared of x. Also, we're remembering that this is a notation with trig functions, that if you have cosine of x squared, usually it's written like this, cosine squared x, with that squared in the middle. We want to sort of be careful because we don't want to get it mixed up with this, which is a different function. This would be cosine of x squared. And so this is how we write cosine times cosine. Okay, this is looking actually more complicated than we want it to be, but we have cosine squared x, and now this will turn into a plus. So this is cosine squared x on the top plus a sine squared x over cosine squared x. So can we cancel these two? No, we absolutely cannot. We cannot cancel something that isn't in each term in the numerator. So those won't cancel, but there's this awesome trig identity that we'll pull up here, cosine squared x plus sine squared x. This is one of the most fundamental trig identities. Cosine squared x plus sine squared x is You probably remember what this is. It's 1. So that's fantastic because the numerator now just turns into 1. This is 1 over cosine squared x. And we don't leave it like that because 1 over cosine x is just secant x. And so if we have 1 over cosine squared x, this is secant squared x. And this is the derivative of tangent of x, secant squared x. We started with y equals tangent of x. We wanted the derivative, and it is secant squared x. So I'm just going to add that to the list of trig derivatives that we know. We'll now say that we know that the derivative of tangent of x is secant squared x. Awesome. Okay, let's try the next one. We won't do all of them, but I do want to do this one, the derivative of secant x. So if y equals secant of x, find dy dx, find the derivative. And this also is a really good one for you to try. You're going to use quotient rule again, and you're going to remember that secant of x is just 1 over cosine of x. Quotient rules, it looks a little different this time because a few things are going to drop out. So go ahead and try this one on your own. Okay, so you've tried this and you've gotten an answer using the quotient rule. Now let's do it together and see if we all got the right answer. So we want the derivative, we want to find the derivative of secant x, and secant x is 1 over cosine of x. And so I'm going to use the quotient rule, low d high. Low is cosine x. D high is 1 and the derivative of 1 is 0. So cosine x times 0 minus high, which is 1, and then the derivative of the low. Derivative of cosine x is negative sine x. All over low squared, cosine squared. And these, definitely some things drop out here. We'll have, well, cosine x times 0 is just 0, and then we have a plus here, and 1 times sine x is just sine x. Oops. So we have sine x over cosine squared x. This isn't usually left in this way. The way that we will write this is going to be recognizing that this is sine x over cosine x times cosine x. Sine over cosine is tangent, so this part is tangent x. And then we're left with, this is tangent x, and then we have essentially a 1 over cosine x, and 1 over cosine x is secant x. So tangent of x times secant x. Or it's usually, this little tiny dot is not usually there. They just say tan x, secant x. And we know that there's a multiplication. Okay, so this is the derivative of secant x is tan secant x, or secant x tan x. We start with y equals secant x, and then we learn that through the quotient rule that this is its derivative. Okay, so now that we're kind of rolling along through these trig functions, let's just write down the ones that we know, and I'll tell you the ones that we don't know yet. Of course, we know these two basic ones, sine and cosine, and then we've discovered that the derivative of tangent of x is secant squared x, and we've also discovered that the derivative of secant x is tangent secant, but it's usually written, just the order is changed, secant tangent x. And then the last two, which we haven't proved, but the proofs are very similar. Cosecant x and the derivative of cotangent x. We could use the quotient rule on either of these. And the derivative of cosecant x is negative cosecant x cotangent x, and the derivative of cotangent x is negative cosecant squared x. So we now have the 6 trig functions and their derivatives. Let's get some practice using these in some sort of mixed problems. So the problem we're going to look at now is to differentiate this function, y equals x cubed sine x tan x. And the reason I love this problem is because we can automatically see that there's going to be some product rule. We've got these sine x and tangent x, so we're going to use our new found knowledge of what the derivative of tangent x is. Can we just go through and say, oh, the derivative is 3x squared, let's see, cosine x, secant squared x? No. Some people will try to do this, but this is totally false. This is not the case. When we have a product, we cannot just simply find the derivatives of the different factors. So this is a big no. Please don't do this, especially on an exam. Okay, so what we're going to have to do is use the product rule. So we'll use the product rule. And you probably can see right now that something else is going on. And the thing that also is going on, we not only have to use the product rule, but we have three terms. So we're going to have to use the product rule twice. So what we're going to do is we're going to say, we sort of have an embedded product rule in a larger product rule. Let's split this up and say these are the two products here, x cubed sine x times tangent x. And we'll invoke the product rule on that. We're remembering that the product rule is regular first, derivative of the second, plus derivative of the first, regular second. And we recognize there are more than two factors, really. We have x cubed times sine x times tangent x. So the product rule gets used multiple times. And when you're first learning this, it can be confusing to know, okay, we know we need to use it multiple times, but how exactly does that happen? And so we're going to treat this as kind of the first part of our product. This is the second part of our product. But then within this first part of the product, we recognize that there will probably be another product rule used. So let's just have the overarching structure be this times this, and we'll invoke the product rule. So the product rule says, so dy dx will be regular first. So this is our first part. So just regular x cubed sine of x. And then product rule says next take the derivative of the second part. So we need the derivative of tangent x. We just learned that this is secant squared x. Okay, and now we have a plus sign. That's easy. Plus sign. Now this is where a second iteration of the product rule is going to be used. We want to find the derivative of the first part, and this is the first part. In finding the derivative of this, we have to invoke another product rule, where now this is the first part and this is the second part. So we're going to do a second product rule where this is the first part and this is the second part. So this product rule says regular first, derivative of the second, plus derivative of the first, 3x squared, and regular second. Okay, so that is just from this little f prime right here when I was taking the derivative of this first part. And then the product rule, our largest product rule, says, okay, now you can take the regular second part, and that will just be tan x. So just kind of reviewing, we really do have these 1, 2, 3, 4 parts. 4 parts to our product rule and this plus sign in the middle. But then within the product rule, we had this additional little product rule that we had to use because we had to break this one up. So, and we can leave it like this. We don't need to simplify. This is the derivative of this original function. So it was good that we recognized that we had 3 factors and that we would be using a larger product rule, but then we would have a little product rule inside of that. All right, let's try another one. This is a good problem because it's throwing together a lot of the different rules that we've been learning. And we have a function and they ask us to find f prime of x, and then later they want us to find f prime of 4. So the derivative evaluated at x equals 4. And I can see a lot going on. First of all, the new trig functions that we've learned derivatives for. It looks like we're going to have a power rule here and a quotient rule here, as well as a product rule. I see a product rule right here. So with all of those rules happening, you think, where do I start? Where do I go first? Well, before we begin, let me say an error that a lot of people will make. They'll just say, okay, I'm going to go through and find the derivative of each of these parts and then put it over, put this division sign in between. Definitely that's not what we can do. We do have to invoke all of the rules. There's a product and a quotient rule that we have to respect is going on. So the largest thing that's happening is this quotient. And within the quotient, there will be a product. So it's the quotient that is the overarching structure that we'll follow the quotient rule to begin with. So f prime of x is, we're going to follow the quotient rule here, and we start by saying low d high. So low part of the quotient is just secant x. So that will be low secant x times the derivative of the high. Okay, so already we're slammed with the derivative of this, which will involve a product rule. So for right this second, I'm just going to say derivative of this. I haven't taken it yet. I'm just going to kind of hold it in place. And then after that, it's minus regular top, or high, minus high, 3x squared cosecant x, times the derivative of the low. And this is not too bad because we know what the derivative of secant of x is. That's just, the derivative of secant of x is just going to be sec tangent. So we can probably just write that one right now. So secant of x, tangent of x. And again, that just came from finding the derivative of the low. All over low squared. So all over secant squared x. And so we're pretty much, we have that this is what f prime of x is, but we still have to go back and do this. The reason I skipped it or kind of pushed it away for a minute is because it involves a product rule. Now, the question I have for you is, do we have to invoke the product rule 3 times? Technically, we have these 3 factors, 3 times x squared times cosecant of x. And I'm going to tell you that no, you don't, because the 3 is just a constant multiple. We have a rule for constant multiples that you can just sort of hold those off to the side and they can be pushed back in after you've taken the derivative. So we're going to treat this as a product rule, and we only have to use product rule 1 time. And the first factor will be 3x squared, and the second factor will be cosecant x. And I'm going to make this yellow so that I can see in my next step where where all that work is happening. Okay, so we have f prime of x equals secant. Oh, I didn't write the x. Secant x. And now I'm going to go ahead and find the derivative of this guy using the product rule. And I'm going to remember the product rule is this guy right here. Okay, so the product rule says to take regular first, and so I'm taking this times this. So regular first will be just 3x squared times the derivative of the second. So we have to remember what the derivative of cosecant is, and it's negative cosecant x cotangent x. Okay, so I have this times this, definitely remembering these parentheses so that this doesn't look like a subtraction. And then to that, I'm going to add, because that's the next thing I do, is this little addition. The derivative of the first, the derivative of 3x squared is just 6x times regular second, which is cosecant x. Okay, so I have done this large quotient rule, and then I needed to do this product rule within, and this is that product rule that's within. I have my 4 pieces. I have this plus this times this. Yeah. Okay, but I still have a bunch of stuff I still need to write because this stuff didn't go away. So I still have a minus 3x squared cosecant x sec tan x all over secant squared x. Okay, and then at this point we have completed the first question, part A. And I'm just going to double check. It always kind of is to your benefit to double check that you did everything. We had this quotient rule. We did low d high minus high d low over low squared. Definitely have everything, and just double checking the product. Regular first, derivative of the second, plus derivative of the first, regular second. Okay, that looks really good. Now the thing I'm really not looking forward to, this was part A. Part B says, okay, evaluate that at 4. And of course, make sure you're in radian mode. You probably are because Desmos default is radian mode. And we're just going to let Desmos do this, but it's still not that fun to type in all of these different guys. So, but it is good practice because it could show up on the exam. So go ahead and try to find this one on your own, f prime of 4 using Desmos. And then I'll stop the video, but then I'll tell you what I got on Desmos. So you've done this long trig calculation in Desmos, and you probably, hopefully, got the same number I did, negative 63.078 for f prime of 4. This is what it looked like when I put it into Desmos. Desmos really does like you to use parentheses around trig arguments, like what you're taking the trig function of, when especially when it's got a bunch of them, because then it is sure what exactly you're taking the cosecant of. Okay. So just to recap, in this problem, they gave us a function and asked us to find the derivative, and then asked us to find the derivative evaluated at a certain x value. When I saw this, I knew that there would be a quotient rule, and it looked to me like there would also be a product rule. You do have to start deciding, okay, what goes first, the product or the quotient? The largest structure in the function is a quotient, and so that's why the largest structure in the derivative is the quotient rule. Embedded inside will be this product rule that's coming from part of your quotient is a product. And we learned, we used the new trig functions that we had learned, their derivatives. I want to end with an application, and this last derivative was kind of a bear to find. This application that we're about to look at it's not a hard derivative to find, but we want to start explaining in the context of the problem what's going on. And here's our problem. When a mass hangs from a spring and is set in motion, the object's position oscillates in a way that the size of the oscillations decrease. All right, let's wrap our head around that first sentence. So there's some object that's hanging from a spring. So here's maybe some platform or a ceiling, and there's a spring. And then at the end of that spring is some kind of object, a mass. And a person can like pull the spring down, and then it goes back up, and then it down, and then up. But over time, those up and downs get smaller and smaller, and it gets back to its equilibrium spot. So we pull it, and then it starts going up and down. So a mass hangs from a spring and is set in motion. The object's position oscillates in a way that the size of the oscillations decrease. Okay, that's what we were just talking about, how it'll go down and then up, but these start getting more and more muted. This is usually called a damped oscillation. Suppose that for a particular object, its displacement from equilibrium, where the object sits at rest, is modeled by this function. Okay, so this function is going to model the displacement over time. Assume that s is measured in inches and t is in seconds. So t is in seconds, s is in inches. So it starts at some equilibrium point, and the equilibrium point at time 0, that's where it's sitting. And then how far off of the equilibrium does it go? It's probably something like this, where you first pull it and it goes way far away from equilibrium, bounces back, but then it starts over time just kind of getting back to where it was in equilibrium. Sketch a graph of this function for t is greater than 0 to see how it represents the situation described. Use Desmos, of course, if you like. Please label the axes. Okay, let's use Desmos and see what this picture looks like. And when I graphed this function in Desmos, this is the picture I got. These are the axes, 0, 0, and of course I don't really care about time before 0, like negative time, so I'm going to actually crop that part of it out. And we'll say we only care when time starts at t equals 0. And we'll see what's going on here. Okay, we have a little bit more fine-tuned picture of what's happening. And so this is our y-axis here. Let's see, let's draw it with... Here's our y-axis, and the vertical axis is representing inches, so displacement, position, s in inches. And then our horizontal axis here is representing time in seconds. And we can see that, it gets pulled apart, and then it actually, the dampening of the oscillations really starts happening quickly. Okay, I'm going to actually take off this big thick green thing because it happens so quickly that within 10 seconds it's pretty much back at equilibrium. Okay, so we did that first part. We did what they asked us to do. Here's question B. B of this problem says, okay, why don't you go ahead and compute ds dt and state the units of this on this function. And this is the question that, this is why it's in this section. So we want to know what s prime of t is, and knowing that this is s of t, it looks like the largest structure of what's happening in this function is it's a quotient. Then we also have a sine function and an exponential function. Will we have to use the product rule? Not really, because even though there's two factors here, one of them is just a constant, and we have the constant multiple rule, which makes things much easier. You wouldn't be penalized if you use the product rule in this case. It would still end up the same, but you would waste some time, and like on an exam, you don't want to waste that time. So please recognize that this is a constant multiplied by a function, so we can just use the constant multiple rule. Okay, so we need quotient rule, so that's low d high, low times the derivative of the high, which is 15 times cosine of t, minus high, 15 sine of t times the derivative of the low. We love e to the t because it's its own derivative. So the derivative of the low is just e to t all over e to the t squared. Quick question, is there a way to simplify this? There absolutely is. When you have a power to a power, then you can just multiply those powers. So this is the same thing as e to the 2t. So e to the 2t. Okay, we have found the derivative. They asked us to, and we just did low d high minus high d low over low squared. We actually didn't use, we could have done this problem back in the last section because cosine and sine, or sine function, we already knew the derivative of, and the quotient rule we already knew the derivative of before we stepped into this section. Okay, let's see what they're asking in part C. Oh, the units. We still need units on this guy. So s prime of t will be all of this stuff. And the units on a derivative are always the output units, inches per second. So this is sort of the instantaneous, this will give us the instantaneous velocity. This is s is just a position function, s prime is a velocity function. Anytime we have a position function, its derivative is the velocity. And this time it's measured in inches per second. Last question on this problem is to compute and interpret s prime of 2. So s prime of 2, we'll just, wherever there's a t, we'll stick a 2 in, and we'll let Desmos do all of this for us. I just found that s prime of 2 is negative 2.6907. So the way that we would interpret this, and this is one of the most important parts of the problem, is we would say this: 2 seconds after a spring is set in motion, the mass or the object is traveling at negative 2.6907 inches per second. They never really say that positive motion is this, and positive position is this, and negative position is this, but that's usually the default. So we could say that it's traveling downward at negative 2.6907 inches per second, and that would be the interpretation. So all of a sudden we know a lot of derivative rules. We know the power rule, which tells us that if we want to take the derivative of x to the n, it's just n comes out front, n times x to the n minus 1. We know the exponential rule, which tells us the derivative of some constant raised to a power. A variable power will be natural log of a times a to the x. We know we use a lot the constant multiple rule, which says if you're trying to take the derivative of some constant times a function, you can actually bring that constant out front and just let it hang out while you take the derivative of the function. Those were the first few rules we learned. Then we use the product and the quotient rules. So product and quotient rules, and now we know all of these trig rules. So we really have a good foundation. The thing that is coming up next, which is really a big deal, is something called the chain rule, and it just opens the world up to a bazillion more derivatives. So next is chain rule, and it relies on composition of functions. So I just want to give you a quick preview to that. Oops. Say that we have y equals sine of 3x squared plus 7. We actually do not know how to take the derivative of this right now. It's because we have a function, 3x squared plus 7, embedded into another function. And I want you to remember how these composition of functions work. If I told you that g of x is 3x squared plus 7, and I told you that f of x is sine of x, could you write this just as a composition of two functions? And I guess the question is it, so does y equal, is y g of f of x? Or is y f of gx? So these are telling us that we're composing two functions, but which one is it? Well, it looks like we put g of x, 3x squared plus 7, in for the variable in f of x. So we were putting g of x into the function f of x. This is definitely the correct interpretation of how we would write that function, and not this one. Okay, so that's just a little tiny preview. We've got some great things coming up when we deal with composition of functions and we use the chain rule. But we've learned a lot already. We're getting some good practice with all of these rules, and hopefully you're feeling a little bit more comfortable with them.